So yeah, again, continue to look at this example right here. So this is the failure rate and the survival rate at the point of 62,500 miles. And you can calculate it using the Excel formula like this. And so this is in order to control the number of within warranty service to less than 3% of the total tires. How much mileage should the firm seek to cover? They only like to cover like less than 3% right here. Okay, so this is a failure rate. We're looking at somewhere here. It's not exactly, we can't really see 3% here. So you actually need to run a calculation using Excel to learn the exact number here. Of course, you can always, take a look at this number right here. They'd like to cover less than 3%. So if they like a whole number, they can just say 58,000. But if they'd like to be more specific, you can always utilize the inverse of normal distribution. So it's a 3% average standard deviation, that it will give you the point. They give you 3% before that point. Okay, so that is the exercise number 2. Here. Yeah, we can discuss this thing later if you are interested in. So far, you feel like we've done nothing different. Everything we've done thus far, something we've done in the past, right? So yeah, exactly. So we in the past trying to get something out of this curve, right? But now you are seeing this thing right here. So in order to utilize the curve, you kind of have to get all the dimensions before the point of interest, okay? But the advantage of this orange curve is that in order to obtain the probability up to that point, you just take a look at the height of this guy right here, okay? So that is convenience. I don't know if you got this, but if you don't get it, you can just move on, okay? So the orange curve is here, right here. It calls as cumulative density function, okay? So at this point tells you the combined probability up to this point of x. However, this blue curve, in order to obtain everything up until this point, you kind of have to take integral. This calculus is headache. Okay, so the reason why you didn't have to take integral so far is because we've been utilizing the Excel function, or either you were able to use the z table to look up the result. So that is why. Okay, but the curve tells you the probability up until that point. Again, the blue curve tells you the general shape, general pattern of this probability distribution. In order to calculate the probability, you actually needed to take integrals. But anyway, we can move on. So we look at the normal distribution and how we can apply that concept in a reliability. However, it is more common when there is a time involved. Okay, when the function, when the reliability is a function of time, mathematically we usually use exponential distribution rather than the normal distribution, because exponential distribution will have a couple of mathematically very, very convenient property, and also represents the time dynamic better than the normal distribution. Therefore, we actually rely on the exponential distribution here. Okay, so let's take a look at exercise number 3 here. A component has a failure rate of this per hour during the normal use. In other words, lambda is 0.006. Okay, please determine the reliability function. Okay, what is the probability of not failing in the first 200 hours, failing the first 100 hours, and failing between, and so forth. So let's, before move on, let's sort it out, okay? First, this problem needs to rely on exponential distribution rather than normal distribution. Okay, we know that lambda is 0.006. Okay, you can also calculate 1 over lambda, of course. And let's convert number 2 in the language of probability, not failing in the first 200 hours. It's not failing within first 200 hours. So this is a probability of failing within the first 200 hours. So this makes it not failing within the first 200 hours. Failing the first hour, this is fairly straightforward. Failing within first 100 hours. Probability of failing between 100 and 150 hours. So this will be the probability of okay, so this is what I'm trying to calculate in here. So let's move on. I need to do a brief recap on exponential distribution. We have learned it in the 30-20. I don't know whether other instructors have gone through this extensively, but at least in my class, I try to provide a very thorough introduction of exponential distribution. So unlike normal distribution has two parameters, average and standard deviation, exponential distribution only have one parameter, which is the average failure rate, lambda. Okay, the shape of the curve is actually determined by the size of lambda. Okay, the variance is actually equal to lambda. It's not that this distribution doesn't have variance. It's just that the average and the variance is the same. That's very convenient. Okay, and the left-hand side of the mass. Left-hand side of the mass. Is there any more? No. Left-hand side of the mass, which is here, okay, can be obtained using Excel formula Dist. Okay, remember, this is the probability of failing within 200 hours. Your left-hand side is the probability of failing before time hit to that point. Okay, consequently, anything after that point or right-hand side of that point is the probability of surviving that point. Therefore, this is reliability at 200 hours. I hope it's clear to you. Okay, so the Excel formula, Exponential Dist, will give you anywhere up until that point. Therefore, this formula tells you the failure rate. Okay, if you want to have the reliability, you can always do 1 minus that to obtain anywhere after that point, which gives you the reliability. Okay, so my description here basically explains that. Okay, so here, the point after x is 30%. So the probability of not failing, even after 200 hours, is 30%. So it means that the chance that it will experience a failure within 200 hours is fairly large at 70%. Okay, 70%. So this is lambda. So average mean time to failure can be calculated this. So 1000 divided by 6, I don't know what the size of this number is, but if you compare this with a 200, then you can tell the plausibility of this result. I think, of course, it's going to be a very, very plausible result. Okay, let me move on. So here, this is your reliability function. I've done the same thing, right? There's no way you can calculate this manually, trust me. Okay, you're always starting from 0 if you'd like to plot it on the Excel, okay? Because the exponential always begin from 0. So lambda is 6, so the mean time to failure is actually 166 hours. So yeah, I think the previous result is pretty plausible here. So 200. So you have 70% chance experiencing failure, which is not too small. You cannot actually ignore the probability that big. But you also have a 30% that's quite large that it's going to survive that point. So for example, if you're preparing for this lamp that need to last 200 hours, okay, I would not use it. I would not use it. So that is what it is. And this is, of course, again, the Excel solution. If you plot this, okay, if you plot this, this is actually the, I think this is a survival curve. I have plotted usage time against the survival probability. So that will give you the exponential curve right here. So here, this area is actually provided by this particular formula, and this area is provided by 1 minus the previous area. Okay, so that is first one, and with that you can easily calculate all these probabilities. If you look at question number 2, not failing in the first 200 hours, right? So your rational approach is 1 minus exponent Dist, which is the failure rate. And question number 3, what is the probability of failing in the first 100 hours? This is asking you the failure rate directly, therefore it's very convenient. And what is the probability of failing between 100 and 150 hours? So this is asking what is the probability that it will fail between 100 and 150 here. What is the chance that it's going to fail between this time slot? And if you look at the Excel formula, it's very easy. Okay, you get this probability first, and then you get this probability next. You subtract it. This is the probability you need, which is here, which is 14%. Okay, I hope this makes sense to you. Yeah, I've done the drawing here already. So, okay, I'll stop this video right here because I need to finish this whole thing in next one shot.